In this example, we're told we have a pressurized water nuclear reactor power plant, shown in the figure. Water vapor is generated in the boiler for use in the turbine condenser pump power cycle. So let me just detail what's going on here. So you have one loop here. This is the loop where the nuclear reaction is occurring. So you have a reactor vessel here with the uranium that's doing a fission reaction. The radiation that's emitted from the uranium goes into heating some fluid in this loop. This could be like a molten salt or something like that, but it's some material that gets heated up to very high temperatures, and it's circulated around with this pump, and that goes into a secondary loop here. In this loop we have water, so that loop is right there. This section's called the boiler, so you have this very hot fluid from the reactor loop that there's some heat exchange to the water here that causes this water to boil, and it turns into steam. So it gets very, very hot, and it goes out here through a turbine. And that high energy steam turns the turbine, and that turbine's connected to a shaft to an electric generator. So this is where your electricity is coming from, and then that goes out into the electrical grid. So the steam goes through the turbine, and then it goes through a thing called a condenser. This is where you'll see this later in the course, but you remove some heat, some residual heat from that steam, and then in this condenser, what happens is it could still be mostly steam coming into the condenser, and it'll cool down and turn back into water, and then you'll have water coming out here. This is a feed water pump that just circulates the water back. Water again here, and then it heats up and turns to steam, and then it just repeats that loop. So there's another loop here. This loop and this loop don't exchange mass. They just exchange energy. They're self-contained, so you don't get any bleed over between like whatever this, molten salts or whatever it is in this loop. It doesn't bleed over into the feed water. Now in this condenser, you'll see there's another loop. So here's a third loop of water let me start here. So you have some cooled water here in this cooling tower. So the water here is at nominally atmospheric temperature. And then it comes into this pump. Here's some makeup water, because as you'll see, you lose a little bit of this water through evaporation. That's what this cloud is. When you see these big cooling towers at the power plants, if this cloud coming out of the cooling tower is nominally white, that means it's just water vapor that's leaving. So it's just this water is evaporating and escaping. So there might be a need for makeup water from a surrounding river or pond or something like that. Anyway, this water is moved by this pump into the condenser, and there's some heat exchange here. So remember this, you've got some still relatively high temperature steam coming out of the turbine, and we want to cool it back down into water so we can continue the loop. So to turn it back into water, we need to cool it down. So that's what's happening here. Some relatively cool water coming in, and then it exchanges energy with this hot water or hot steam, and then this warm water gets hot again. So it's now warm. It's taken some of the energy from this water in the condenser, and it cycles through and then is sprayed downward, and then just atmospheric air kind of goes through the cooling tower and cools that water down, and then it gets back to atmospheric temperature here. So this is a third loop this way. And again, there's some makeup water that needs to be added because there's some evaporation as it's sprayed here. This is not entirely enclosed, and so you get some escape of water there. So there are three different loops here. They're all separate from one another. Okay, so that's a kind of a long explanation of what's happening. But in part A, we're asked to consider a control volume surrounding the cooling tower. So let's draw that in there. Draw it in red. Identify the locations on the control volume boundary where the control volume interacts with the surroundings and the directions of flow. So show the energy flow diagram. So we'll draw a control volume that surrounds the cooling tower like this. It's always important to identify your control volume so everybody knows what you're analyzing. As far as the energy flow diagrams, we need to keep track of where there's some energy exchange as well as mass flow rate exchange. So let's do the mass flow rate exchange. Here we have some mass flow rate coming in from the water in this cooling loop here. So there's a mass flow rate coming in through the pipe here. There'll be some mass flow rate coming out right here. And then we said that there's some evaporation of that water occurring during the spray. That's also going out through the top. I'll just call this evap, so some evaporation. So you can see, these are all the different, well, actually there might be a little bit, let me draw one more. So I've just drawn this in terms of the water. There's actually some air that will come in. Normally these cooling towers, it's not shown very well here, but normally there are inlets for air to come in through here. So I'll just do it as mass flow rate of air coming in. That occurs near the bottom, and then there'll be some air that comes out through the top as well. Now, in steady state operation of this cooling tower, the mass flow rate of air coming in and going out would be the same. The mass flow rate of water coming in should equal the mass flow rate that's been evaporated and the mass flow rate that goes out. So to keep this cycle with a constant amount of mass, whatever gets evaporated here, you'd have to use the makeup water to make it, so that the mass flow rate at this point is the same as the mass flow rate there, right? So ideally we would have the same mass flow rate of water through this whole thing, but some gets evaporated, so we have to bring in some extra makeup water. So anyway, this is the mass flow rate in and out of the control volume here. There is a little bit of energy transfer, I would assume, that's occurring here. There's probably some heat transfer occurring along the walls of the cooling tower because it's warm in here, but that's probably negligible. The temperature of the water here is not that high, so there's probably very little heat transfer occurring through the walls here. There is energy escaping from this cooling tower because of the evaporated water. It'll carry some energy out with it here, but it's not like a rotating shaft or electrical work or heat transfer. It's just because the water here probably has a little bit of elevated temperature compared to the water here, for example. So anyway, for part A, this is everything we need to show. Now for part B, we're asked to repeat for the containment structure and the electrical generator as the control volume. So we're going to do this, we're doing this in two different groups here. So let's do the containment structure first. So we'll draw a control volume there, surrounding the whole structure. Here, the mass flow rate exchanges are here, where we have some mass flow rate of water coming in through that cooling loop, and then here we have the mass flow rate of water going out. Now, since this is an entirely closed loop, this mass flow rate and that mass flow rate would be the same in steady state operation. And as far as the mass exchange, that's it. That's the only place where you have mass coming in and out of that out of the containment structure. This whole loop is entirely contained within the inside, so we don't have to worry about that. We are only keeping track of what crosses the boundary. As far as energy crossing the boundary here, I'll assume that the containment structure is pretty well insulated, so there's very little heat transfer going on across that boundary. So we wouldn't worry about that. And there are no rotating shafts going across this boundary, so we wouldn't worry about that. There's probably some electrical work coming into this, so I'll just draw it here. Because we have the pump inside here, so I'm going to just assume that there's a wire, there's some wire coming out to run that electrical pump, and whatever electronics are going on inside that containment structure. So there's probably some electrical power that's going in through the boundary here. Okay, and then the next one was to draw an energy flow diagram around the electric generator. So that one is right here. Here there's no mass flow rate that's crossing the boundary. It's an electric generator, but we do have different kinds of power crossing the boundary. Of course, we have electrical power going out here, and then we have shaft power going out. It's going in. So it's going from the turbine into the electrical generator. So I'll just write that as W dot shaft. Again, the whole function of this power plant is to turn this turbine so that it rotates the shaft of the electric generator and creates electricity. So the power is going into the electric generator as shaft power, and it goes out as electrical power. Often electric generators get pretty hot, so there's probably some heat transfer to the surroundings. I'll draw it as Q dot. That's the rate of heat transfer to the surroundings there. It's an energy transfer. That occurs when this surface gets pretty hot compared to the surroundings, so there'll be some energy exchange that way. So that covers this example. And just a reminder, we draw these energy flow diagrams like what I've shown here in these three different devices. We draw those because once we've drawn them, then we start writing out equations for conservation of mass and the first law and the second law. It's very equivalent to drawing free body diagrams and then applying Newton's second law to those free body diagrams. So it's the same exact idea, except instead of dealing with forces, we're dealing here with energy exchanges and mass exchanges. So we start our analysis with these kind of drawings first, and then our equations are based on the drawings. Okay, we'll end the example there.